So second derivative, you're doing the derivative of the first derivative, right? And so we know if a derivative is positive, it's increasing. But if we're looking at the second derivative, if the derivative is positive, that means the first derivative was increasing, not the original function. It's actually what's giving us concavity. So if we look at some scenarios here, we have two different graphs, right? If this is my function, if I drew my tangent lines, okay, can we agree that the first derivative would be positive here? Okay. And this one, can we agree the first derivative would also be positive? Okay, but the second derivatives are different because the second derivative tells us how the slope of those lines change. When I look at this one, these lines are becoming more steep, right? So they are increasing. That means the second derivative is positive. This one, these lines are getting less steep, so their slopes are decreasing. So that's when the second derivative is negative. Now this actually has to do with the curve of the graph. This is what we call concave up. It's curving upward. Think about if you filled, if you finished it off with this hold water.
Yes.
Yes, that's concave up. This is called concave down. If we finish it off, does it hold water? No, it's curving downward. So that is concavity. So if the second derivative is positive, the graph is concave up. If the second derivative is negative, it's concave down. That's what I put out to the side there, our concavity test. So first blank is concave up, second blank is your concave down. I'm good with this. So we're looking at a graph. This figure shows a population of honeybees. How does the rate of the population increase change over time? When is this rate the highest? Over what intervals is it concave up and concave down? So first let's address, how is this changing over time? What would you tell me? It increases the entire time. Okay. Okay. So the population always increases. Is it faster at the beginning or end?
Right.
Yeah. Got off to a slow start, but then it accelerated pretty quickly in the middle, and then by the end it's flattening off. It's still rising, but not much.
It's hitting that carrying capacity.
Ooh. Pulling some
Pull
bio
back,
here.
pull back all the way from sophomore year biology.
There's probably some limiting nutrient.
When is this rate the highest?
At the end.
Well, the rate, not the number of bees.
Oh, at like 12.
When it's the most vertical, so somewhere, do you think, between 9 and 12?
Like 10.
Somewhere in there.
11.
I'm just going to say between 9 and 12 weeks. But you can be more precise if you want to approximate it. Somewhere in there, we hit that point where it was increasing most rapidly. The third question, concave up and concave down. Where is this concave upward?
From 0 to...
0 to about 11. Okay. When is it concave down?
11 to...
Okay. So notice you guys have said 11 a couple times.
It's not critical. Oh my gosh, it's a focal point.
Kind of.
What does that say?
About 11 weeks. So a critical point is when the first derivative is 0. That's a max or a min. This is a critical point of the first derivative.
A critical point?
When the concavity changes, it's called an inflection point.
Oh, yeah.
So in 11 is an inflection point. It's a point where your concavity changes. where we change from concave up to concave down. And it's essentially just finding a critical point of the first derivative instead of the function itself. So we're looking at when the first derivative is 0 or undefined. And again, those inflection points. Did every critical point give us a max or a min? No. So will every inflection point be a change in concavity? No, but it's where it might occur. All right. There is what's called a second derivative test, and I'm not a huge fan of it. I don't really use it, but some people might like it, so I didn't want to just skip it. I really like the first derivative test. We have our points. It's easy to think if we're going up and then going down, we get a max. The second derivative test is a little less intuitive, and it doesn't always work. It tells us if your first derivative is 0. So if the first derivative is 0, that means it could be a max or a min, right? So if it's a max or min. And if the second derivative is positive, that means it's curving upward. Then was it a max or a min?
Curving upward means a min.
Yes. So if you have the first derivative is 0, so it means it has to be either a max or min. The second derivative is positive, so that means it's curving upward, then that point had to be a min. If your first derivative is 0, so max or min, and it's curving downward, that gives us a max. Now, the downside of this, sometimes your critical points and inflection points happen at the same number, so they might both occur when x is 0. And in that case, the second derivative test doesn't help us. So I don't use it a lot. I pretty much rely on the first derivative test to decide increasing, decreasing, max, min, but this is another option.
So the second derivative being greater or less than 0 is
The concavity, how it's curving.
So if it's always like this, it's always going to be minimum.
All right. Let's have a good thought-provoking question.
I don't want to do this.
This looks scary.
Sketch a possible graph that satisfies the following conditions. And I have a typo here. On the second condition, it should say f of prime of x is greater than 0. But I just didn't want to retype the whole thing, so we're just going to fix it. Yes.
Oh, I was looking.
So I left off the greater than 0 on yours. That's what you need to fix. All right. We are making some graph that fits this requirement. Some graph, probably not the only graph, just one option. So the first condition. The first derivative is greater than 0. If the first derivative is greater than 0, what does that tell us about our graph? It's not positive, but it's increasing. If your derivative is positive, the graph was increasing from negative infinity to 1. So I know that my graph has to be going up until I get to 1. Make straight lines here. So this is probably something we're going to tweak as we go, but currently all I know is until I get to 1, my graph is rising. Now, is that set in stone right now what I just drew? Absolutely not. We're going to figure out what it means. The first derivative is less than 0. What does that mean? Okay. So after 1, it's going to be decreasing. So what happens at 1? The max, right? It's a critical point. We are getting a local max here. Okay. So far, what I've drawn would work, but we know we're not done. Number 2, the second derivative is less than 0 from negative infinity to negative 2. Sorry, greater than 0. On negative infinity to negative 2. So until I get to negative 2, my graph is, the second derivative positive tells me concave up. So until I get to 2, I know my graph has to be increasing, right? We've said that, but it's curving upward. Okay? between -2 and +2, I'm going to jump over for a second. My graph is going to be what?
Computer down.
Yeah, the second derivative is less than 0 between -2 and 2, so it's curving downward. Alright, so I need to fix my graph as I go. I know I still have to be rising, but it's got to be curving downward. Okay, at 1 I have to have my max, but still curving downward until we get to 2. So I'm slowly adjusting my line. Right, and after 2, my graph is back to being
Computer down.
it still has to be decreasing, but it's curving upward. Because it tells me here it was concave up on -infinity to -2 and to infinity. Okay, so currently this graph meets all the requirements. These places, -2 and +2, that's where my graph kind of switched. A lot of times when we're graphing by hand, we'll put little X's there to kind of show us this is where our curvature is changing. The third, at the limit as x goes to -infinity is -2.
So it hits -2 on the y.
Tells me -2 is a
Horizontal axis.
horizontal asymptote. Okay, so I'm gonna have to adjust my graph again. So much for that. It was a good shot, but my graph went down too low.
I basically did that.
So we know that it has to change curvature at 2. So we're curving down, and then we're gonna curve up and get the approaching.
I think my graph looks right, but I'm wrong.
I just had to adjust mine because it went below my asymptote. I was trying to make it hit that asymptote. And the limit as you approach infinity is 0. So we have a horizontal asymptote at 0 in this way. So what do I have to do to fix my graph?
Make it approach.
Yep, I just have to pull this. It still has to be curving upward and decreasing, but it's more like that. Okay, is this beautiful? Absolutely not. We had to tweak it a lot. But we're starting to understand when we read these requirements, what they're telling us, where we have maxes or mins, what it means to be increasing, decreasing, to have our concavity.
Oh man. If we do that on our own, I'm sure.
Yeah, everybody.
We're not going to do it on your own today.
Not today.
We'll get there.
Tomorrow, what? We won't have school tomorrow.
I don't know. Current tracks have changed. Now they've dropped our snowfall maps.
Oh, I'm still
It's
feeling
back
no
down to
school.
1 to 3 now.
Yeah, it's still enough.
I'm feeling a lot of
That's
ice.
Carson
I haven't
is.
seen anything about ice.
Elsa.
A lot of.
What is it?
All right, let's do concavity.
2 derivatives got a double derivative without.
So, here is my function. F of x equals. So if I do my derivative, or my first derivative of x cubed is,
3x squared minus 6x.
if I want concavity,
Do it again.
then second derivative.
6 minus 6.
Then we need to find when this is 0 or undefined. Is it ever undefined?
No.
No, but it's
Positive
0 at 1.
Okay. So this is what's called an inflection point. It's when your first derivative is 0. Or sorry, when your second derivative is 0. Critical point is first,
I can't wait to get that confused.
inflection point is the second.
It's like anytime you say something wrong, my brain's like, that's the right answer.
Sorry, I tried not to.
It's okay.
I corrected myself.
Why are you being perfect?
I will
Yeah,
try to do
what
better.
is this?
I've let you down.
Oh, we have to drop this too.
We need to know when we're concave up and down, so we're going to do a sine line, but we're doing it for the second derivative. So we're going to plug our test points into the second derivative. Remember when we started this and I said good labeling is really important here? This is where we need to label.
Oh.
You need to know the difference between your first and second derivatives. Okay, so if I put in a 0,
That was so good.
Zero.
Notice for Carson.
minus 6 is -6.
Why is it for Carson?
If I put in a 2, 12 minus 6 is a positive. So this tells me my graph is concave down where?
Well,
Negative infinity. 0 to 1, sorry. And then from 1 to
Okay,
okay.
So, checking concavity is just like what we were doing yesterday with increasing and decreasing, but with the second derivative.
That's pretty easy, I think we.
Yeah, I think we should just
on the
skip
homework,
9.
okay.
Skip 9? But
I
this
think-
is our first experience of graphing everything.
I
That's
know.
fine.
That's
no,
why I wanna skip it.
It's
We're,
okay.
we're gonna do everything now.
Oh, no.
Gonna start graphing these things.
No.
The way Carson's like buffered.
Okay, here we go. I want concavity inflection points, maxes and mins on this and a graph. So, labeling, super important. First derivative is what? Okay. So if I set that equal to 0, I could take out a 4x squared. Gives me x minus 3. So what are my critical points?
0, 3.
Now, if I want to find maxes and mins, increasing and decreasing, what do I have to do from that?
That's fine.
So smaller than 0, in between 0 and 3, bigger than 3. So if I put in -1, -1 squared is positive, -1 minus 3 is negative, so this section is negative. I put in a 1. 4 times 1 squared is positive, 1 minus 3 is negative, so it's still negative. Why did I get the same sign twice in a row?
Because it's a fake math.
Oh.
Because it was a square that multiplied.
Oh, I thought you were asking
Oh, it's a
for like.
bounce. No, it's not one. No.
Bounce if we were graphing like a
Yeah.
polynomial.
Yeah, but it's.
So it can happen. Don't just assume you always alternate signs. There are different things that could make us get the same sign twice.
Well, we alternate here.
If I put in a 4, we get positive. Okay. So there's 2 things you can tell me right now.
We have the max.
We have,
Nope, min. I mean,
this was decreasing the whole time, but at 3, I went from decreasing to increasing. So we have a local min. Do you guys do order pairs or function notation?
I do
All of
order
the above.
pairs.
Alright, you can do either. If you play in 3, how do you get the y value?
Plug it in the original.
The original. So 3 to the 4th would be 81 minus 4 times 27. So negative 27.
I believe you.
I believe you.
Is there a max on this one?
No.
Okay, so I've got my min. Increasing and decreasing. Where's my graph increasing?
3 to
3 to infinity.
Where is it decreasing?
Negative infinity to 3.
We don't have to break it 0 because
Doesn't
It's-
change.
it doesn't change here. Now, if it were something like 0 was a point where the graph was undefined, then you would have to say negative infinity to 0, union 0 to 3. But because my function's continuous, we can just put it all together. Alright, that's the stuff we were finding yesterday. I also want inflection points and concavity. So now we need,
The second derivative, 12x squared minus 24x.
alright, so there's my first, so my second will give us 12x squared is 24x. And we need to figure out when this is 0. We take out 12x. And pull these inflection points. Please, when we have these questions, like test or quiz, it'll be like 1 question per page. Please don't make me search for all of your stuff. Like, box it in so I can tell.
Oh.
Label what's what.
You can just
Help
go to
me
the-
out.
1 question per page?
Yeah.
How many?
Part A, part B, if you like.
No, I know. How many pages?
Oh my goodness.
No,
I haven't written the test
in
yet.
my head, I'm
22.
picturing like just like this, how this is written, but like a sheet of paper, like top to bottom. There could be words.
It's just in a book.
Okay. So we need our sign line. So smaller than 0, between 0 and 2, bigger than 2. Alright, so if I plug -1, where am I plugging these in?
The second derivative.
Right, everything I'm doing right now is based off the second derivative. We already did all of the first derivative work. So 12 times -1 is negative, -1 minus 2 is negative, negative times negative is positive. I put in a 1, 12 times 1 is positive, 1 minus 2 is negative, positive times negative. If I put in 3, I get positive times positive.
Oh yes.
So, my graph is concave up where?
Negative infinity to 0, and then union 2 to infinity.
And concave down?
0 to 2. Oh yeah. I think I'm kind of locked.
Alright,
Homework time.
now let's graph it.
Oh.
Oh.
Mm-hmm.
Oh.
I thought Carson was doing that as a bit, and then I realized he didn't read that part.
No, I was hoping she would forget. We
Now you sound like my daughter.
Right.
Wait, we're supposed to graph -27?
Sure.
I'm gonna count by 3s or 9s or something.
Just mark it. Just.
Yeah, I don't
We
know.
don't have to
I don't
be
know the
like
last time I counted on the
super precise, but we do need to maybe not just put a random dot somewhere. Let's make an effort. So we know our min is at 3, -27. I'll just count by tens. Yeah, but we have multiple points that we need to plot, so let's actually use a scale. So 3 and -27. Alright, I also want to mark my inflection points. We have them written as x equals, but if I'm going to put them on my graph, we need the ordered pairs. How do I get the y's?
Plug it back into the original.
Alright, if we put 0 into the original, we get,
Wait, that's a max?
no,
Wait, why did I put max? It's min. Yeah, that's
Oh.
0 is what you get when you plug.
for inflection points, I mark them as an x on our graph. Okay, so 0, 0 is an inflection point, I'm going to put an x there. If I put in a 2, so we get 16 minus 16. So 2, -16. That's why I didn't just want you to put a random dot and call it -27. So we're trying to make these as accurate as possible. So inflection points are x's. Alright, so now we just have to draw the graph. We know this is a local min. We know to start our graph, it is decreasing and curved upwards. So decreasing, you have two options. It could be falling like this or like this.
It's
The
concave
first
But
up,
it's concave up, so it's that first one.
then.
So it's falling, coming in, my little X there.
Supination.
Decreasing but curving upward. Okay, my graph has to continue decreasing until we get to 3. But we know between 0 and 2, our graph is curving downward. Okay, it's not a drastic change, it's kind of like a cube graph. You know, this slightly changed. This is curving downward. You can maybe make it a little more pronounced than mine, but it's not significant. That's why we put those X's to show us where it's changing. All right. And then we have to be concave upward for the rest of the graph. We're still decreasing. And then after this point, we are increasing but still curving upwards. So it looks like. And we just drew our first polynomial graph with all accurate information.
It's terrible. That's icky.
It's kind of fun.
Wait, so do you want us to put the X's then?
Yes.
For the,
Yes.
for the
It helps me a lot when I'm trying to tell, because concavity shifts, it's not like a drastic max or min that you can easily see. It happens precisely here. So So if I can see those points, that gives me a little more grace when I'm
Wait,
trying to look at your stuff.
so do calculators do all of this?
Mm-hmm.
How far down do they go into the derivatives?
Well, their approach is more like the table of values. So if you plot all the correct points, like every point, you get this naturally.
Oh,
But we are shortcutting just making a table of values for everything.
okay.
All right.